7.4, Day 2, continues with work using sum and difference formulas. In our first example, prove mathematically that sine 120 plus 45 doesn't equal, when you split it up to sine 120 plus sine 45, would you please section off that problem so that we can use the space on the right to help us with that bottom example. There's not quite enough space for both. To prove mathematically that sine 120 plus 45 isn't the same as just sine 120 plus just sine 45, this is very similar to the worksheet from yesterday. When we have a parenthesis, this is that u plus v definition, or the sum formula for sine. When we have just plain sine 120 and sine 45, those are both already on the unit circle, so we're not splitting them up at all. On the left side, we need to expand. Let's take that sine formula and do that. Sine u plus v would expand to sine u, which would be sine 120, but then times cosine v, which is 45. And for the sum formula with sine, it's plus when we expand it. And then we take cosine 120 times sine 45. So there's more to work with when we have the parenthesis using that definition. From the unit circle, we have sine 120, which is square root 3 over 2, times cosine 45, which is square root 2 over 2. And then just plain, or cosine 120, going back over there, is negative 1/2, and then sine 45, square root 2 over 2. Now remember, when we multiply fractions, we multiply straight across on top and bottom. And you can multiply the insides for the square roots. That gives us square root 6 over 4 plus negative 1 times 2 is negative square root 2 over 4, which we could actually write it as an addition problem, or I would like to see it just written as a subtraction problem. Square root 6 plus negative square root 2 is just square root 6 minus square root 2 over 4. And remember, we're going to get lots of answers that look similar to this. Now, if we try to figure out why it's not the exact same as when you just have the terms individually, we are allowed to go right to the unit circle with sine 120. And that just means we're going to be at square root 3 over 2. And I'm not multiplying that by anything, so if I add sine 45 to it, that's square root 2 over 2. To add, we have a common denominator, but recognizing that the numerators aren't like terms, we get square root 3 plus square root 2 all over 2. And that would be the answer on that right-hand side. This validates that we can't just split it up into two parts. We have to expand when we have that parenthesis option. What's going to make this next example a little bit tricky to navigate is that I want us to find the exact value of sine u plus v, and we're going to find tangent u minus v. So we're going to do two examples in this space. And then notice the rest of it. This is where it gets a little tricky. It says given sine u equals 4/5, where u is between 0 and pi over 2, and cosine v is equal to negative 12/13, and that's between pi over 2 and pi. This means we're going to need two pictures, so we're going to draw our pictures up above. That's why I wanted you to have some of that space to work with. So what we need to do is draw a picture for angle u. Whoopsie, I'm going to get that focused here. There we go. Draw a picture for u and a picture for v. So I'm just going to kind of arrow up so that you recognize later that's where these pictures are coming from. If angle u is between 0 and pi over 2, that means it's in quadrant 1. So I'm going to draw a picture to represent that in quadrant 1. I'll put my hypotenuse somewhere and drop my right angle straight down to that x-axis. Now, the weird thing about this is that the angle is the angle is u in that corner. And that's going to be how we'll determine our trig definitions. So if we keep reading, I'm just going to even this out a little bit because it bothers me. Here we go. Let's fix that here. Hang on. Okay, that's better. It says the sine u is 4/5, so that means opposite over hypotenuse is 4/5. Now, a little Pythagorean theorem to get that missing side length, or if you already know it, that's great too. 4 squared is 16, and 5 squared is 25. If we move 16 over, we get a squared equals 9. And if we take the square root, a equals 3. And because we're in quadrant 1, all of our side lengths should be positive, which means a will equal 3. Right underneath this now, I'd like you to write the 3 kind of most basic definitions for our trig functions. Sine u, we already know that answer, is 4/5. And we're going to use that in our expansions down below. Cosine u, be careful, it's not negative 12/13, that's cosine v. Cosine u is 3/5. And we're going to need tangent u, so tan u is equal to 4/3. We're going to use all 3 of those fractions instead of the unit circle. Now, over to the right, we're going to do the same thing for triangle V, or angle V. It says angle V is between pi over 2 and pi, and that would indicate that's in quadrant 2. Oh, I want that in black, though. I want that to match. Hang on. Okay, so that would be in quadrant 2, and that's going to affect some of our trig definitions. Up top, then, if I draw my picture, we're just going to create a coordinate system like we did for the first one, and I'm just going to make it a little bit bigger over here in quadrant 2, draw my hypotenuse up, and then connect that right angle down. And now my angle is right here. That's angle V. Now it says cosine is negative 12/13. Cosine is adjacent over hypotenuse. Recognizing that the hypotenuse is always positive, that means the x-coordinate is going to be negative 12 to get a cosine value that's negative. Now if we do a squared plus b squared equals c squared, watch that negative 12. A squared would stay as is. Negative 12 squared is positive 144, and then 13 squared is 169. If we move 144 over, I'm not sure what I'm doing there. There we go. Nope. Let's fix that. All right, so minus 144. We get a squared equals 25, and when we take the square root, a will equal 5. Now counting up on the y-axis in quadrant 2, it's fair to say that a is positive 5. And just like on that left-hand side, let's go ahead and define our 3 trig terms that will be useful for us down below. There I go again. Sine v, sorry everybody, make sure that's a v, is opposite over hypotenuse, so 5/13. Cosine v, we already know that one. That's negative 12/13. Tan v is going to be negative 5/12. Now these fractions are the only fractions we're going to work with when we expand down below. And notice I wrote we have 2 options to evaluate, sine u plus v and tan 2 minus v. So we're just going to do this one first as a, and then we'll do this one second as our b. If I want to evaluate the sum formula for sine, truly everybody, the first thing you have to do is expand. So just write that in all capital letters. And when we expand, it's important to know you're not doing anything with those fractions yet. Absolutely nothing. We're expanding with the u and the v. So we're really just rewriting the formula. Sine u plus v is the same as sine u times cosine v, and then plus cosine u and sine v. Make sure you write it in that form first, because then sine u, that whole thing is the fraction. U isn't the fraction, but the sine value is. That makes it positive 4/5 times cosine v was that negative 12/13. So notice in this row, everybody, the trig term goes away when we evaluate the definition. Cosine u, well, if we go back up to our u triangle, cosine u is positive 3/5. Sine v is positive 5/13. Like so. Now these are products, so we're going to multiply them together. And the great thing about doing it in this format is that you automatically get common denominators in this step. 4 times negative 12 is negative 48. 5 times 13 is 65. 3 times 5 is 15. And 5 times 13 is 65. To add fractions with common denominators, we just add the numerator together, and we get negative 33 over 65. Based on the given information and where we plotted our triangles, sine u plus v would equal negative 33/65. All right, let's do example B, that new one that we're going to add on. Our next expansion is tangent u minus v. Now, anything with tangent is always going to be particular. And if you look at the definition for the difference formula, notice it becomes a fraction. It's tan u minus tan v in the numerator all over 1 plus their product, tan u times tan v. This is going to require a bit of work, so let's see what we've got. It says tan u. If we look up top, tan u is 4/3 minus tan v, which is negative 5/12, all over 1 plus the product, 4/3 times negative 5/12. Now, in the numerator, to subtract those fractions, we need a common denominator. So we have 3 and 12. Therefore, if I multiply that first fraction by 4 over 4, that would give me 16/12. And then we have two negatives that make a positive, so plus 5/12, and that gives us 21/12. So I guess that wasn't so awful. In the denominator, if we multiply, now we can just multiply straight across. So we have 1, and then 4 times negative 5 is negative 20, so I'm going to do minus 20 over 3 times 12, which is 36. Well, in order to subtract these, again, we need that common denominator. 1 is the same as 1 over 1. So if I just multiply 36 on top and 36 on bottom, we would get our common denominator. 36 minus 20. Whoops, I don't know why I'm writing that right now. Hang on. So if we just do 36 minus 20, that would give us 16 over 36. I guess I didn't need my fraction bar so big. Now, if we have a compound fraction like this, in order for us to simplify, we're going to multiply by the reciprocal of the denominator. So we're going to do that keep, switch, flip method. Keep the first fraction, so 21 over 12. Switch divide to multiply, and flip the second fraction, 36 over 16. Now, we could multiply top and bottom and try to simplify that fraction, but if you recognize something about products with fractions, any numerator can reduce with any denominator. So I recognize 12 and 36, that 12 would go into 36 3 times and into itself once, and that reduces pretty quickly. Now the 3 and the 16 wouldn't reduce further, and 16 doesn't have a factor that's with 21. So now if we multiply it straight across, 21 times 3 is 63, over 1 times 16, which is 16. That would be the difference formula for tangent. In the last section, we're just going to do a little bit more work with expanding, and we're going to go back to our unit circle. So anytime you have a parenthesis, remember to expand your definition first. Cosine theta minus 3 pi over 2. This would be the difference formula for cosine u minus v. If we use our definition on the other page, u minus v breaks down into cosine u, which would be theta, times cosine v, which is 3 pi over 2. And then if it's minus in the parenthesis, we have to remember for cosine, it's plus in the expansion. And then it's sine u, which would be sine theta, sine v, which would be sine 3 pi over 2. Now, the first two answers, or the first two terms in each pair, have theta in them, which we're going to leave as is. But in the second term, we can evaluate looking at the unit circle. 3 pi over 2 is all the way at the bottom. So if we take cosine theta times cosine at 3 pi over 2, cosine at 3 pi over 2 is 0. And then if we do the same thing for sine, sine theta, down at the bottom on the unit circle at 3 pi over 2, sine equals negative 1. Now cosine theta times 0 just cancels out. And sine theta times negative 1 just equals negative sine theta. And since we don't know what theta equals, that's the final answer, negative sine theta. So expanding the definition, keeping theta in our work. Let's try the next one. Tangent 3 pi plus theta. So 3 pi plus theta, that's u plus v. And here goes our fun tangent definition. If it's plus in the definition, it's plus in the top of the fraction. So tan u plus tan v all over 1 minus their product, tan 3 pi, which is tan u, times tan v, which is tan theta. So if we think in the unit circle, 3 pi, remember all the way around is 2 pi. Therefore, to get to 3 pi, we'd have to go to that left-hand side. So now we're going to be over on the circle on this left-hand side. And tangent equals 0. That makes this pretty easy to work with. We'll take it. So if we say equals, tan at 3 pi is just 0, plus tan theta, over 1 minus, again, tan 3 pi, 0, times tan theta. Well, if we have 0 plus tan theta in the numerator, that just gives us tan theta. And on the bottom, 0 times tan theta crosses off, and 1 minus 0 is just 1. Our answer here then, tan theta divided by 1, is just tan theta. And that's as far as you can go. For our final example, sine pi over 3 plus theta. So there's our u plus v. When we expand the sum formula for sine, it's sine u, which is sine pi over 3, and then it's cosine v, which is cosine theta. If it's the sum formula for sine, it expands as an addition problem, and then cosine u, which is pi over 3, sine v, which is theta. Going back to that fun unit circle that we all know and love so well, at pi over 3 in quadrant 1, sine equals square root 3 over 2. So this one gets a little weird. I'll show you why in just a minute. Times cosine theta, nothing changes. And then plus, if we take cosine at pi over 3, that's 1/2, times sine theta. Unlike the last two problems, nothing cancels out here. That means our answer is this sum, since they're not like terms. Square root 3 over 2 times cosine theta plus 1/2 sine theta. And here's your second half for the notes on 7.4.